So, dear students, in this video, we are going to form the stiffness matrix for given coordinates. So, I have taken one member subjected to a moment at A, moment at B, and the reaction at A and reaction at B. So, we have VA and VB. And I am assuming the direction. If you are given with some different direction, you should consider that direction for your formulation of stiffness matrix. Actually, the stiffness matrix is basically defined by load per unit deflection where delta equal to 1, or in beam like cases moment per unit rotation where theta equal to 1, which is defined by stiffness. And if you are want to formulate the stiffness matrix for this coordinates, so you have to first of all mark the coordinate orders. I am going to consider this moment as 1, the right side moment as 2, and the left side reaction as 3, and right side reaction as 4. So you should not change the order while assembling the stiffness influence coefficients. So what is stiffness influence coefficients? We can write K11. So the stiffness influence coefficient is Kij, where J is the point of loading and I is the point of response or effect. So J is the point of application of load, I is the point of the coordinate of application of J is the coordinate of application of load, I is the coordinate or the point of response which we are observing. So if you write K11 and K21 and K31 and K41 in one column, it means that you are applying a unit rotation at the coordinate 1 and you are observing the effect on the other coordinates. That is, I can draw the diagram as K11 means you are applying a unit rotation at 1 and you are measuring or observing the response at 1. And here it is K21, you are applying a unit rotation at 1 and you are measuring or observing the response at 2. Similarly, you have to find the responses in all the coordinates, given coordinates. Because why I am telling given coordinate means even they can omit some of the coordinate from this diagram and even they ask to form the stiffness matrix. For the second coordinate, you are applying a unit rotation at 2, that is, and you are measuring the response at 2. Here you are applying a unit rotation at 2 and measuring the response at 1. And here you are applying a unit rotation at 2 and measuring the response at 3. You are applying a unit rotation at 2 and measuring the response at 4. Similarly, you can assemble the values of stiffness matrix. For the second one, it is K12, K22, and K32, K42, K13, K23, K33, K43, and K14, K24, K34, K44. So now let us complete this stiffness matrix form. So we are going to calculate all these values for the given problem. So first of all, from the slope deflection equation, you can recall this slope deflection equation MAB equal to M bar AB plus 2EI by L into 2 theta A plus theta B minus 3 del by L So this is the basic slope deflection equation. If you are omitting this fixed end moment and you multiply the coefficient inside 4ei theta a by L, 2ei theta b by L, and 6ei 6ei delta by L square. So you have to remember the individual components are the moment components. So this is one of the moment component and this 2ei is one of the moment component and the 6ei del by L square is one of the moment component. And we can write individually m equal to 4ei theta by L and another moment equal to 2ei theta by L. If you are considering left side moment and applying a unit rotation means the moment will be created as 4ei by L in A point. At the same time, half of the moment will be carried over to the B point. So it is 2EA theta by L. And due to the support sinking, due to some settlement, because in our given problem, we are applying a unit rotation and here also the moment is correlated with rotation and you can correlate this reaction in the upward direction with the support settlement, If you push this point, if you push this point B, it will go upside. So it will create some delta deflection. If you consider this is fixed, you can have some deflection curve like this and you can draw the moment causing the deflection is like this because if you understand if some point making delta deflection means the moment will be created like this to make delta deflection at this point B and at A support the point is considered to be fixed because other ends are considered to be fixed. So the moment should be formed like this to keep this support as a fixed one. If you consider both the directions are clockwise. Both the directions will be the same. If you want a delta deflection here, this is the moment direction. And if you want the support A is to be rigid and the clockwise moment is the possible moment. Because if you apply a moment here, it will lead to some deflection. It will lead to some rotation here. It will try to lift up this member. So it is not possible to get a fixed support at this point. If you want to, if you try to resist this deflection at a point, this is the moment direction. Okay. Individually, you consider for the delta deflection, the moment is 6EI del by L square. So you have to remember these three components while formulating the stiffness matrix because a moment is related to the shear force because if you consider the same moment direction, I am applying like this because you may come across this case in moment distribution method by calculating the horizontal reaction and I am assuming HA is in this direction and HB is in this direction and if you are consider moment at A, moment at B, you can take moment at B to calculate HA. So if you take moment at B equal to 0, so if you have some height h for this, what is the reaction? You take the moment at this point. First of all, you consider the direction. MA is, I am considering MA is positive. This direction is positive. So MA. HA is opposite to this direction. So minus HA. And we need the perpendicular distance to convert HA into a moment because MA is already a moment value. So there is no need of multiplying the distance. Here HA should be multiplied with the perpendicular distance HA into H. and MP is also considered to be rotate in the same direction of MA. So plus MA equal to 0 because HB needs to multiply with perpendicular distance. If you take moment from this point, there is no perpendicular distance to multiply with the HB. So we should not include HB in our equation. So the possible components added in this equation is MA and HA, and also you should include MB. So HA equal to MA plus MB by H. So it indicates that the assumed direction of HA is correct. Assumed direction of HA is correct. Then there is no external load. So HA will be contracted by HB in this opposite direction. If HA is towards right, HB is towards left. In this case, I am assuming the direction the same way I am assuming it is also correct. MA will give the downward reaction and MB will give the upward reaction at B. Okay. So now you have to remember these three components and let us start applying a unit rotation at A. So this is our component. So if you apply unit rotation at 1, what is the moment component formula here? First of all, you remember at A, it will create 4EA theta by L. And you are considering theta equal to 1. Then m by theta equal to 4EI by L, where theta equal to 1. So m by theta is the definition for stiffness. So the K value is 4EI by L. So the moment created by theta is equal to K11 equal to 4EI by L. On the other end, half of the moment will be created, that is 2EI by L into theta, which is also a moment component, and you convert m by theta equal to 2EI by L. So theta equal to 1. So 2EI by L is the stiffness value. So here at B support, so K21 equal to 2EI by L. So we have calculated K11 and K21. We need to calculate K31 and K41. Actually, we can derive one concept, that is, what is moment? Moment equal to force into perpendicular distance. Perpendicular distance. And in other words, we can write moment equal to reaction into the distance d, distance d. If you want reaction, it can be rewritten as moment by the distance. It is otherwise can be written as span. So moment equal to force into perpendicular distance, where force, that is reaction, equal to moment by span. And the reaction can be calculated as summation of moment by span. Summation of moment by span. So we can calculate VA as summation of moment by span. We have two moment, 4EI by L and 2EI by L, and you add 4EI by L plus 2EI by L divided by span. So this is a common denominator, so you can add 6EI by L divided by L. So finally you will have 6EI by L square. So this is VA. What is VB? There is no external load, so it is minus 6EI I by L square, or otherwise if it is downward direction, VB will be upward direction. So here I am marking the direction as downward and upward, so no need to consider this minus. So we can write only the format 6EI by L square, here also 6EI by L square. So first step, it is finished. We have calculated all the stiffness coefficients by applying theta A equal to 1. So this is first uh, subdivision. Second subdivision, similarly, you can apply here theta equal to 1. So at B point, there will be a moment 4ei by L into theta. So theta equal to 1. So the stiffness K22 is equal to 4ei by L. Due to the unit rotation at second coordinate, we will have the first stiffness matrix, that is rotation coordinate, is half of the moment will carry over, so 2ei by L. And if you look at um, the reactions, the same reactions, that is summation of moment by span, same 6ei by L square will be here, 6ei by L square, 6ei by L square. So we can represent as 3,2, which is K42. Next one, the third subdivision, you apply here unit displacement, because up to this step we are considering unit rotation because it is a moment. It is a moment, so we can apply only unit rotation. Here it is a force. It is a force. So the moment is related with theta and force is related with the deflection. So you apply a unit deflection here, delta equal to 1. So other ends are considered to be fixed. So this frame will be deflect like this. So the moment created will be like this. So what is the moment created due to support settlement delta? So m equal to 6ei delta by L square. It is from slope deflection equation. So if it is delta equal to 1, m by delta equal to 6ei by L square, where delta equal to 1. So the moment here is 6ei by L square. Here also 6ei by L square. To consider the direction of moment, initially we assumed the direction of coordinates is like this, and the reaction coordinates are like this. If you get the same type of direction as a response, you should consider it is a positive quantity. The moment here is the same direction with the assumed coordinate in the given problem. Okay. Now it is the moment value. We have the reaction here. Actually, this is K. K 13. Here it is K 23. We need to calculate K 33. Here K 43 we need to calculate, because these two are moment components. So I am naming it as K 13 and K 23. We need to calculate the reactions. How we can calculate summation of moment by span equal to the reaction. So what is the moment values here? 68 L by 68 by L square, 68 by L square. So 6ei by L square plus 6ei by L square divided by span is L. So you will have 12ei by L cube. If it is VA, then VB equal to opposite direction. VA is downward, 12ei by L cube, and VB is equal to upward, 12ei by L cube. So 12ei by L cube. Here also 12ei by L cube for the third case. Let us move on to the fourth case, and you will get some a better idea. Here, the displacement should be considered in this direction, the unit displacement. So I am going to apply a unit displacement in this direction, and other ends are considered to be fixed. So draw the deflection curve and try to draw the moment created the same direction as the previous one, and the reaction direction will be like this. So we already knew that the moment due to the support sinking is 6ei by L square. Here also 6ei by L square, and the reaction due to this moment equal to summation of moment by span is equal to the reaction VA. So which is 12 6ei by L square plus 6EI by L square as in the case of previous subdivision VA, which is equal to 12EI by L cube, and VA is equal to minus VB, same 12EI by L cube. Here the directions are reversed, so no need to put my negative value. We just put the magnitude of the reactions, that is 12EI by L cube. Now you mark the representation, which is K, it is due to fourth coordinate effect. So K14, K24, K34 and K44. Now you can assemble the stiffness matrix for the given problem. So K11 from the previous steps, it is actually here. K11 is 4EA by L, 21 is 2EA by L, and the corresponding reactions. So I can write 4EI by L. So next one, K21, which is 2EI by L. K31 is 6EI by L square, and K41 is also 6EI by L square. Okay. Okay, you can put the negative sign for the downward direction and positive sign for the upward direction. Okay. For the next one, you are applying a unit rotation at B, so that you will get this value. I'm going to assemble, that is here you will get 2EI by L, that is K 1 2, K22 is 4EI by L, and it is also downward, so minus 6EI by L square and plus 6EI by L square. I'm considering downward direction as a negative, upward direction as a positive. Next one, for the third coordinate, you are applying a unit displacement at A, so that you will get the moment 6A by L square. Both are clockwise, so you consider it is a positive quantity, and the reactions are 12EI by L cube. So it is 6EI by L square at A and 6EI by L square at B, and the support reactions are 12 minus 12EI by L cube and plus 12EI by L cube. And the next is also by L cube, sorry, L square, 6EI by here actually, okay, clockwise moment only. Here anti-clockwise moment. 12EI by L cube and 12EI by. So this is the overall stiffness matrix. Here the directions can be differ. Some problem they will consider anti-clockwise as a positive quantity, so that the upward reaction is a, negative quantity. So we are assuming the coordinates clockwise moment. Here it is downward, here it is upward reaction. So I am considering the downward is negative and upward is positive. If both the moments are positive, I am considering it is a positive value. So in this manner, I have arranged the stiffness matrix.